we present the application of software aging monitoring and software rejuvenation for the assessment of high availability systems. In such systems, the metric of interest is the transient performability during system recovery, also referred as the survivability metric. A survivability assessment requires the definition of a failure model. In addition, extensive testing using loads and configurations that are able to model the conditions customers will encounter in production is required. We start by describing the application of Markov modeling to software architecture optimization using an attack model and a failure history. We then generalize the approach to the modeling of a high availability system. The approach for architecture optimization uses an existing architecture, a failure history, and an attack history. The output of the architecture optimization process is an improved system architecture. The security model is divided into 3 phases. In phase 1, the node is isolated and no network propagation is occurring. In phase 2, the network is compromised and attacks spreads. In phase 3, the attack causes suspicious behavior. The goal of the architecture improvement process is to recommend architecture investments. The inputs to the process are an existing system architecture, an attack model, and a failure history. First, we'll focus on the failure recovery model. The failure recovery model is a phase recovery where the system can be in each of the states shown in the Markov model picture. In state P, the system is prone to failure. We consider 2 types of failures: hard failures and soft failures. Soft failures are recoverable using rejuvenation. Hard failures can be recovered using one of several strategies, as shown in states F1, F2, and F3. In state F1, the process has failed and is amenable to a process restart. In state F2, the process has failed and is amenable to automated failover. In state F3, the process has failed and is not amenable to automated failover. Therefore, a manual recovery is required. To deal with soft failures, software aging monitoring and software rejuvenation can be implemented, as represented by the states R, X, F, and 0. In state R, the system is under rejuvenation. In state 0, the process is fully recovered. And in state SF, a soft failure was detected. The second part of the architecture improvement process is the security model. The goal of the security model is to assess infection and contagion probability. The attack model is composed of three phases. In phase 1, a single node is impacted because of an initial breach. In phase 2, attack propagates to other nodes. In phase 3, the attack causes suspicious behavior. The output of the security model is the assessment of countermeasures in terms of quarantine probability and software rejuvenation. In phase 1, an initial attack occurs and no network propagation is occurring. The system can be in one of the states shown in the figure. In state A, rejuvenation can occur due to false positive. In state 0, the system is in normal state and is susceptible to attacks. Lambda is the exogenous attack rate. In state P, the system is prone to failure. And in state R, the system is being rejuvenated. State Q represents a situation where the system is in quarantine. In this phase 1 model, there are no endogenous infections. In phase 2, we have exogenous and endogenous infections. The endogenous infections are shown by the rate beta. In phase 3, attacks cause suspicious behavior. And we show here that in phase 3 we have different rates of transitions because of the different detections and attacks. The most important conclusions from this analysis is that the network infection can be extinguished when exogenous infection rate is small. This slide shows how important it is to contain the travel from infected regions to non-infected regions, as for example, in the case of COVID-19 epidemics. This slide shows the increase and decrease in quarantine probability as a function of scanning for severe impacts. It shows how the quarantine probability behaves as a function of the scanning for severe impacts. In the case of COVID-19, it shows the importance of testing, tracing, and quarantine. We now integrate all these different models presented into the modeling of a high availability system in a DevOps environment using agile process. We are required to integrate planning, development, performance testing, and operations. Our method involves the following steps, which embrace development and operations. Each step is based on its predecessor output. First, analysis of ticket history generated by operations is used to create a Markov chain design, which generates a performance test case design. Then performance test case execution is used to parameterize the Markov chain using test case results. The evaluation of the performance metrics of interests provides the basis for the performance checks. And then new software can be delivered to operations based on the performance check. The development team receives feedback on performance issues and bugs and provides new releases for performance checking and testing. As a result of these steps, the following Markov chain was designed. This Markov chain for high availability system is very similar to the previous Markov chains you have shown in pieces, but it includes several additional states to model the possibility of partial failure with aging and a partial failure with no aging, and several different states for the high availability. Here we have additional states for the failover depending on the architecture of the system, where we have also a share blob store and manual repair of a failed host. The lessons learned from this application is that several high availability strategies such as automated load balancing and software rejuvenation require that failures be detected in an efficient manner. We have found that high availability strategies implemented for fast failure recovery also need to focus on implementing strategies for fast failure detection. As in our experiments, failure recovery rates were dominated by the failure detection time. We believe that this finding can be used to help high availability system architects select which software aging and rejuvenation features to add to their high availability design.